What is up, Flash Physics Nation? We are here for another Cliff Notes session. Cliff Notes are, again, us just doing a holistic approach to all of the content we learned in a unit. We are back here today with Unit 2, which is Dynamics. But there was also an extension of Unit 2, and that was uniform circular motion. So we did a whole chapter on uniform circular motion, but really that's just one big section of dynamics, or a big application of dynamics. I learned a few things from my last video. I can't write something down and then erase it, because then it just erases it altogether. So I will note that as we go forward into this series of videos. So with that said, here is a look at our cheat sheet for Unit 2 for the dynamics portion. And if I go forth to the next slide, here is the application portion of Unit 2, and this is all of the uniform circular motion stuff. So you see almost just as much stuff on uniform circular motion as we did on dynamics. Actually, honestly, there's a lot more on uniform circular motion than what we did on dynamics. So we're going to walk through that today and in this section right here. So I'm going to start this with the question, and this is the same question that I ended the last unit with. When I have my formula here, right, I got xf equals xi plus vi delta t plus 1/2 a delta t squared, right? That's a formula. It tells me about displacement. It tells me about distance or position. It explains a change in velocity known as our acceleration. And acceleration then is causing this change in velocity. So then we asked ourselves the question, or I asked you the question, what causes acceleration? And acceleration, our last definition, a very simple definition, is a change in velocity over time. Acceleration is defined as a change in velocity over time. So what causes acceleration? And this actually goes back, it was incorrectly done by Aristotle. Aristotle said a constant force is required to keep an object in constant velocity. And Newton said, no, that's wrong. He actually examined like an arrow flying through the air, right? An arrow flying through the air has a relatively constant velocity in the x direction, but there's no force acting on it. And that got into Unit 2, which is known as dynamics. So dynamics is a very fancy word of saying forces. So it's examining forces that are acting on an object. And the question is, what's a force? Well, it's either a push or it's a pull. And we have different varieties of forces. We can have forces that are contact forces, meaning that they physically touch you, or we can have long-range forces. So long-range forces don't actually physically have to touch you. Things like gravity, things like magnetism. So the very first thing we did was build a catalog of forces. So the very first thing we did was build this catalog of forces. Now we did this to start off, but we also talked about Newton's laws, and we'll get to that in just a second. So let's build ourselves first a catalog of forces. We have things like the weight force, right? Just mass times gravity. So anytime I have a force, I put a hat on it or a vector on it. Remember, a vector is an arrow that shows both magnitude and direction. So we talked about weight, and that's just mass times gravity, right? You have mass, it's always the same. Where you are, meaning planet-wise, that changes your weight. Now, we talked about when something is sitting on a surface, the weight is pulling it down, and the normal force is pushing it back up. And that's equal and opposite, this gets a little confusing, to the weight in the y direction. We could be pulling something with a rope, and that's tension. What's our formula for tension? We don't have one. It's however much you're pulling it, right? We could just have a general force, which we just label as an F. We can have, and then I could add subscripts for that if I wanted to. I could say, oh, it's a force of a push, right? We talked about things like thrust, so the force of thrust. So thrust is it's actually an action-reaction pair, which we'll get into in Newton's third law. But that is like a rocket expels exhaust down to push it up. We got into like spring forces, and a spring force is like if I stretch or compress a spring. There's a what's called a restoring force that is always equal and opposite to the magnitude of the force that's stretching it, or otherwise known as K delta x, the spring constant times the displacement. And there is a negative sign that's kind of a placeholder. It just says that it's opposite in the direction that you stretch or compress it. We talked about the drag force a little bit, and we talked about that more hypothetically, but that's 1/2 rho drag coefficient cross-sectional area times the velocity squared. So when I'm flying through the air, I'm pushing molecules out of the way, and that slows me down. And for the most part, we're, going to ignore that. Later on in the end of the year, we will talk about the electric force, which is Coulomb's law, right? K Q1 Q2 over R squared. Depending on when you're watching this video, you have no idea what I'm talking about. We talked about the gravitational force. We talked about that when we got into chapter 6, and that is the force any two massive objects are attracted to each other, which is different than the electric force, because if I have two charged objects, they could be attractive or repulsive. The gravitational force is always attractive. And G and K, I should have capitalized this actually. G and K are constants. G is Newton's gravitational constant. That's, of course, 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. No, I don't have that written down. K is Coulomb's constant, 8.99 times 10 to the 9th Newton meter squared per coulomb squared. So they're just two constants. And then there was one other big category of stuff that we talked about, and that is, of course, friction. So friction, there are different types of friction, and this is what got a little confusing, right? If I'm pushing something and it's sliding across the ground, it's encountering some type of friction. We call that friction kinetic friction. So kinetic friction is the friction in motion, and instead of using F subscript friction, because there's different types of friction, we use that little f, the fancy F, and we do a subscript of K because it's kinetic friction. And this has a constant value. It's the coefficient of kinetic friction times the normal force. So what gets a little confusing with this, if we're doing stuff on angles, then the normal force is not equal and opposite to the weight. So it's a component of the normal force. So that was kinetic friction. We also talked about, like, if I push a fridge, for example, the hardest thing is getting the fridge going, and that's static friction. And this is the most confusing because it's got a kind of a weird definite or formula. Static friction is always equal and opposite to whatever force you are applying until you break static friction. So really, our only formula that we have, and stick with me on this, right? We have a maximum static friction. And when we break static friction, then instantaneously we're going to be in kinetic friction. So the maximum static friction is going to be greater than or equal to whatever our actual static friction is at that time. And if I increase the static friction, then I'm going to increase the maximum. If I increase the force that I apply, I am increasing the static friction until the object starts moving and I break static friction. And that formula for the maximum static friction is the same formula as before. It's the coefficient of static friction times the normal force. So that gets a little weird, but we're all right. So the last type of friction is rolling friction. And rolling friction is like a ball or a sphere, right? It rotates. So it has some kind of instantaneous static friction because it's not sliding, it's rotating. But those values are actually much smaller. So the coefficients of rolling friction, so same formula, except with an R for rolling, the coefficients of rolling friction are actually really quite small. Like steel on steel is something like 0.008. It's very small. And again, with our coefficients, so we use the Greek letter mu to show that it's a coefficient. These are dimensionless units. They do not have meters or newtons or anything like that. They just have, it's just a number. It's just a multiplier. Okay, so we built this catalog of forces, and then we had to get into what do we do with forces. And how we're going to start to examine forces is by looking at Newton's laws. Newton has 3 laws that govern motion. The first law is the law of inertia. And the law of inertia states that an object in motion tends to stay in motion. An object at rest tends to stay at rest unless an outside force acts upon it. So if it's in motion, if a car is moving, it's going to keep moving unless a force acts upon it. So yes, a car will eventually slow down because of friction. If a fridge is at rest, it's going to stay at rest until somebody pushes it. So that's Newton's first law. And we'll get mathematically in just a little bit with that. Newton's second law is probably one of his most famous equations, and that is F equals ma. And that is my very famous line for this is forces cause acceleration. So when I have multiple forces acting on an object, a better way of writing this is that the acceleration equals the net force divided by the mass. So as I have forces, which are push or pulls, acting on an object, it will undergo a acceleration that is directly proportional to the forces and inversely proportional to the masses. So forces we already know are measured in newtons. If I push 1 kilogram object on a rough surface with 10 newtons of force versus a 10 kilogram object on a rough surface with 10 newtons of force, the 1 kilogram one has a lower mass, so it'll have a higher acceleration. And what is the net force? Well, that's just the sum of whatever forces I have going on. And there could be infinite forces going on. So we'll talk about that in just a little bit. Newton's third law is the law of action-reaction pairs. And this gets a little confusing because it helps us understand some stuff, but it also it states that all forces exist as an action-reaction pair, not at all. So if I push on the wall pushes back on me. That helps kind of explain our next portion when we're talking about stuff, but it can get a little confusing, but there are some further applications of it. So what do we do with these 3 laws? Well, our tool for this unit to play around with these laws is by making free body diagrams. Now, this is not to be confused with later in the year when we talk about rotational motion, and then we talk about rigid body diagrams. So with free body diagrams, we simplify our object. So let's say we got a car. Here's my car. It's my truck again. And it's being towed by a rope connected to a tow truck at, let's say it's at a 30-degree angle. And it's being towed. All right, let's leave it like that. It's being towed. And we're curious about, based on this, the forces that are acting and what they do. And what do forces cause? Well, forces cause acceleration. So what we're going to do is we're going to examine everything that's going on, and we're going to take this complex truck and we're going to simplify it as a particle. And again, this is the difference between the free body diagram and a rigid body diagram. We do not simplify a rigid body diagram as a particle because it no longer falls into the particle model. So what force or forces are acting on the truck? Well, we have its weight, right? It's on wheels, but there's still going to be some amount of friction. We'll call that some rolling friction. It's being towed at an angle of 30 degrees, so there's some tension acting at an angle of 30 degrees, and there's a normal force. Now, this is a quick drawing. Is this drawing accurate is something I can ask myself. And if I can't answer that, then I didn't draw it right. Because although these are qualitative diagrams, they should tell me, or they should show me what's going on. And here's what I see. Let's say that this tension is drawn correctly. It's got an X component of tension, and it's got a Y component of tension. So I could actually, and you should never do this on an AP exam, you're not supposed to draw components, but if I were to break my tension down to Tx and to Ty, the way that I do that is by using T cosine theta and T sine theta. So Tx is T cosine theta, Ty is T sine theta. So I can break things down into components. And visually speaking, if I drew this correctly, which I'm assuming I did, what can I say about Tx compared to its, this is going in the positive x direction, then I have the force of rolling friction going in the negative x direction. Well, just by looking at the length of these, or, of course, by using actual numbers, Tx is greater than the force of rolling friction. What does that mean? Well, that means there's a net force, and that net force is going to cause acceleration. So this object, this truck, this particle, is accelerating to the right. And the reason that it's accelerating to the right is that there is a net force. What about in the y direction? I got Ty and the normal force. If I drew it close enough, these two should add together and be equal and opposite to the weight. So let me redraw it down here. Here's my weight. I got Ty. I got the normal force. And these are kind of arbitrary right now. But the point is, if it's not accelerating in the y direction, then there's no net force in the y direction. So these forces, the normal force and the y component of the tension, should be equal and opposite to the weight. And then I use, to set these up, I use our very favorite Newton's law. I say the sum of the, oops, hold on, let me undo that. The sum of the forces in the x direction equals the net force equals mass times acceleration in the x direction. And you should get sick of saying that. But what does that mean? It means I take all of the forces in the x direction. In the positive x direction, I have Tx. In the negative x direction, I have the force of rolling friction, and that equals mass times acceleration. So this is how, if I rearrange for acceleration in the x direction, it's the tension in the x direction minus the force of kinetic friction all over the mass. This is how I can solve for acceleration in a system. Now, similarly, let's take a quick look, because we can, at the y direction. The sum of the forces, wow, that was a great sigma, in the y direction equals the same thing, equals the net force equals mass times acceleration in the y direction. And some of you might say instantaneously that equals 0, because we know that it's not accelerating in the y direction, and that's okay. Now, what can I do with this? I can say Ty minus the normal force equals the weight. I'm sorry, Ty plus the normal force equals the weight, because it's Ty minus the normal plus the normal force minus the weight equals 0. So Ty plus the normal force equals the weight. There's many things I can do with this. But if I'm missing something in my x direction over here, I could solve for like t, for example, and then with t solve for tx and plug that in over here. So this is where we got into systems of equations and using two formulas to solve for two unknowns. So there's a lot of things we could do with that. And that's really about it for Newton's laws. Right, we have the Newton's first law is the law of equilibrium. That's what's happening in the x direction. Or I'm sorry, the law of inertia. And then Newton's second law is acceleration is caused by a net force. So we can look at these mathematically, and there is a lot that we can do with it. Now, there was one quick application that I talked about, and that is getting into the concept of the mass of a system. So when we start expanding our view, and here's what I got for you. I got a table. We did this lab, right? I got a track on this table. I have a low friction pulley and a cart on it, right? That low friction pulley is tied off to a mass. Now, one last tweak to this formula is that the sum of the forces equals the mass of the system times the acceleration of the system. So what's happening here is I have a cart, and this cart has some mass. This mass here has some mass. And because it's no friction, it's going to cause the cart to accelerate. So how much mass I hang from this matters, the rate of acceleration. How much mass the cart is matters, and it affects the rate of the acceleration. So the net force in this case is actually this hanging mass. So we'll call this mass 1, we'll call this mass C. So the sum of the forces, what force, well, remember this is called an Atwood machine, and we kind of modify this and we say this is our positive x direction. Well, the sum of the forces in the positive x direction is the weight of 1, and in the negative x direction, on that first guy, right, so I draw free body diagrams for each one. I got the weight 1, and I got tension, and weight should be larger. That tension is equal and opposite to the tension on this little cart, and if we can assume that there's no friction on this cart, that's the only force that's acting in the x direction. It also has its own weight of the cart and the normal force of the cart, and those two are balanced. So when I come back to my equation, it's the weight minus the tension for this guy right here. But in the positive x direction up here, I have plus tension. And these got a little confusing for some of you because you're like, why is tension on there twice? Because it's in each free body diagram. And this whole thing equals the mass of the system times the acceleration of the system. And my tensions do cancel out, but that means my acceleration of the system equals the weight of the first guy divided by the weight of the cart plus the weight that's hanging. So both masses need to be taken into account, because the more mass that I put on this cart, the greater the weight of the cart is, the less this acceleration is. And that's an important thing. It's not all objects are going to accelerate at the same rate because of this hanging mass. It's how much mass they have because of the inertia that they have also matters. And that was pretty much it for the first part of dynamics before we got into uniform circular motion. Now, a big application of dynamics, and we treat it as just part of it, but really as can be its own standalone unit, is this concept of uniform circular motion. And we have a whole nother cheat sheet dedicated to this. And the concept with uniform circular motion is, I'm going to draw something as viewed from above. So this is like a ring stand in the middle, and the very first thing I did was I tied a dune buggy, and that dune buggy goes around in the circle as best of a circle as I could draw. I could use the shape tool, but that just doesn't sound like it's a good use of time. So that dune buggy is going in a circle. Now, it is going, because it's a dune buggy, we know that it has a uniform speed. So it has a velocity that wants to go straight. But with that velocity, there is tension going into the middle. And that tension is causing it to not go in a straight line. So the question I ask, and this is how we said, this is how we talked about it, speed. What's going on with the speed? Well, it's a dune buggy, so that speed is constant. Does that mean that the velocity is also constant? And the answer is no, because velocity has speed and direction. So the velocity is always changing. Okay, so if it has a change in velocity, by definition, we have to have acceleration. And acceleration in this case it's a constant magnitude of acceleration. So it's constant magnitude, but the direction is always into the center of the circle. So we could use this to talk about quite a few different things, but what we got from it and we have this concept of centripetal acceleration then, and the formula for that is v squared over r. So the magnitude of the acceleration is v squared over r. And then what's causing that acceleration? Well, it's the tension that's causing that acceleration. What causes acceleration? Oh yeah, forces. So we get F net still, but instead of ma, it's still ma, but it's ma centripetal, so it is mv squared over r. So when an object is going in a circle at a constant speed, it has uniform acceleration going towards the center of the circle, and the force that's providing it is the magnitude mv squared over r. So there's a lot of stuff that we talked about with this. We kind of tweaked our way of quantifying it because, well, the velocity, the speed, sure, it's going 3 meters per second, but it's always going in a circle. So we talked about a couple different things. We talked about the concept of frequency. Frequency is the number of cycles that it makes every second. And we talked about period. And the period is the amount of time it takes to make one complete revolution. And these two things are inversely related to one another. So frequency is cycles per second. Period is time in seconds for one cycle. So we talked about that. We also brought up this concept of angular velocity, which we talk about in radians per second, where one complete circle, so the angular displacement in one circle is 2 pi radians. So we got into that as well, and we got a ton of different formulas for that. So that was the basics of circular motion, but where we really hit were some applications. So some of these applications we talked about, a big concept was apparent weight. So if I'm going over a hill, well, there's a net force towards the center of the circle, that's my weight. And since there's a net force, it has to be larger than my normal force. So when I go over a hill, I feel, because the concept of apparent weight is equal to the normal force, I feel lighter. If I go fast enough, I can feel weightless. I could also go in a dip, and the dip is the opposite, where my weight is going down, but my normal force is actually going up in towards the center of the circle, so it's larger. So I feel heavier when I go over I feel heavier when I go into a dip. Now, we also talked about, well, let's talk, getting into roller coasters. Let's go back to this concept. But what if we're going around a circle, right? Then I have to have my weight going down. And we talked about a couple things with this. If I'm going in a circle fast enough, I also have this normal force going down. So I could feel still heavy, but if I'm going just fast enough that the normal force doesn't exist, so I'm going fast enough through this circle that there is no normal force. We call that our critical velocity. That critical velocity is the minimum speed needed to make it around the circle. It's not zero. It's a minimum speed that, quote unquote, this weight is balanced out by a new concept that we talked about, and that is the centrifugal force. Now, the centrifugal force is not a real force, but it explains a lot of stuff that's going on. So like if I'm in a car, if I'm in the passenger seat of a car and someone takes a rapid left turn, I feel like I'm being thrown to the right. And the reason for this is not because there's an actual force, the centrifugal force pushing me to the right, but rather it's my inertia. My inertia wants to keep going forward. The car is turning to the left, so I'm trying to keep going forward, which in my perception is being thrown to the right. So that's a big application, is this concept of centrifugal force. Things that use this concept, the centrifuge, right? The centrifuge spins something around in a circle, and in biology we use centrifuges to separate blood out into its components. We also have this concept of the human centrifuge, which spins in a circle to simulate G-forces for people who are training to be an astronaut or a pilot. So there are a lot of smaller applications that get into it. Another huge application we got into this then was orbits. So I'm actually going to pop up our formula sheet again. And what you see here is everything we talked about with circular motion. So in the middle section here, this is all like the critical velocity, the apparent weight, right? On the left hand side, I have all the basics behind it. We talk about going in a circle, speed's constant, direction's changing. We have all these new formulas for acceleration. We talk about period and frequency. And then we got into this concept of circular orbits and weightlessness. So like getting into orbit, you need a critical velocity that counteracts gravity. We also got into Newton's law of gravity, which is any two objects that are attracted to each other are going to experience this attractive force. But when we get into the applications of that, we have gravity and orbits. So things that are orbiting one another, and we did a long lab, the My Solar System simulation, and we looked at all these different things. We can, again, get into quantifying it. And that's what really physics is, and we've talked about this, is that physics is the quantification of an explanation of the phenomenon of life. So as we understand more, we can start to explain real life phenomenon that are occurring because of our things that we're studying. So that's why I always like physics. Nobody has to ask me, why are we doing this? What is this? What does this pertain to in real life? Because it pertains to everything in real life. And then the more we know in physics, the more we can explain actual real phenomena. So that's all I'm really going to get into for the uniform circular motion portion. It's just one big application of dynamics. So we'll actually end with that. This whole unit is just about utilizing Newton's laws to explain, and utilizing forces to explain the concept of acceleration, and then we can use that to translate back into kinematics and use our kinematic equations, now understanding a greater depth of forces. So a lot going on in this unit. It was another long unit with a lot of small concepts, but all linking back to these big concepts that is, of course, Newton's laws. So that's all I got for this recap video. I hope it was helpful. And we'll continue our discussion, our third unit, which it kind of helps some of this, because going back to the concept, well, what if I'm on an angle, right? And now I have a normal force here, and it's some component, right? But what happens, I'm sorry if you can't see this that well, but what happens if I have something like a hill, right? I'm traversing this hill as I'm going down. Well, my normal force is always changing, so my acceleration is always changing. So we got into a new concept, or a different way to quantify that, and that is using the conservation of energy. And we'll take a look at that in the next segment.